Welcome to Breadboarding. In the previous video, we managed to get the floppy disk controller that we added here a couple of videos ago, and the floppy disk drive here starting to boot MS-DOS 330, but we weren't quite able to finish booting the operating system. In fact, we ended up with a disk boot failure. This indicates that the boot sector has been read off the floppy disk drive, but then the operating system has not successfully loaded completely. And in this video, what I'm going to be doing is showing you a few more fixes I had to make so that it could actually boot up MS-DOS 330 and also MS-DOS 5. So this is video number 20 in the Breadboard PC 8088 version 2 series, and this is the third video on getting the floppy disk controller up and running. So in the previous video, video 19, which will be a link at the top of the screen up here, which if you want to know how operating systems boot off floppy disk drives, then there was quite a low level dig into that. And did a number of fixes, and we were just trying to boot up MS-DOS 330 and basically just the io.sys, ms.sys and command.com were on the floppy disk, nothing else on there, just to keep things simple. And we did a number of fixes. There was one thing I did notice that when I was reviewing the video afterwards, that in this particular screen, whereas one of the fixes I was talking about, where we were reading a status register, reading the data, going back to check the status again, and I said it was 6 milliseconds, but in fact it was 6 microseconds. So the problem we had here was that from reading the data here to checking the status was too quick, and it actually caused an error because the status hadn't changed by the time we'd got to the last result. Now, I've got some new fixes I've done in this video. So one of the things I needed to do in the first series is we were using a slightly slower clock speed. So we were overclocking the original 8088 up to about 5.3 megahertz. Whereas because this chip we're using is a modern one, we can actually run it at about 8.39 megahertz. So that's the 25 megahertz dot clock frequency we're using for the video card divided by 3. And in the original series, I had to turn off wait states just to speed things up. But in this particular one, because things are running that bit faster, I actually needed to enable wait state. So let's just have a look and see what that actually involved doing. So it's actually a problem with the PLD configuration. So the ready wait speaker PLD is actually used to generate the signals for this. And you can see there's a few fixes I had to make. The clock input wasn't quite identified as an input, and because this is using an ATF750C, there are a few things I needed to do. I got rid of the internal pin node, so I was using an external pin, and I needed to go in and make a few changes, so to use the IO input from the pin in place of just the name for the pin, defining the reset. And with those fixes and explicitly saying that the clock input was an input, so disabling output enable and enabling the others, by programming that I was then able to actually get that up and running. We just have a look what we needed to do. So over here we can see this is our ATF 750C ready wait state, and this actually does a number of things for the speaker, for driving the speaker here, but also has the clock input signal and generates the ready wait delay for whenever we have an IO read or an IO write. Then basically this extends those by providing a ready wait signal here that comes all the way down to our bus controller here. And this is effectively the combined clock controller bus controller. And by providing the ready wait going high here, we'll actually delay the cycle, so we extend it slightly. And what this results in, if we connect that ready wait output into the AEN1, then now we should find our IO read and IO writes will go from 220 odd nanoseconds up to about 340, 350. And here are some logic analyzer outputs. This is the one from the previous video. We can see here, if we look down the bottom, this is the period when we're looking at the IO read. And we can see up here that in fact that was about 230 nanoseconds, the read period, between these two things down here. And now, having made that change, we can now see that this IO read period here between these two timing markers here is now 350 nanoseconds. That seems to have stabilized things. Things were probably a little bit too quick before. So this seems to have stabilized the floppy disk controller side of things. I was also looking at a couple of other issues. So I've improved the decoupling capacitors around the floppy disk controller. So reading some of the documentation on the PLDs recommend using a higher value. We normally use 0.1 microfarads decoupling capacitors, but the Atmel documentation recommended a slightly higher one. And I also added an electrolytic capacitor on the power supply as well. There were some issues, the real-time clock. If you remember seeing the failure screen a few slides earlier, you'll see that there was an error reading the checksum from the non-volatile RAM. This is the CMOS memory that's on the real-time clock. And so I was getting some problems with this. It didn't generally cause too many issues, but having any sort of error like this is always going to potentially be a cause of some problems further on down the line. To fix some issues regarding that, there's still some spikes on the floppy disk controller chip enable signals, and I did some investigation on that. I got a couple of slides coming up which I'll talk about that. It's not fully resolved, but it has been improved. I should also say that as a separate thing, a couple of people have left some comments to let me know about Microchip have actually made a new version of WinCUPL available, WinCUPL II, and this is now available in beta. So you can actually download that from this URL here. And you'll see here you can download a zip of the beta. It's made available on the 20th of August. Now I have actually used this a little bit. I will perhaps do an update video on the PLD series, but you can see here that we can actually set all the compiler options. Main difference between the previous version and this version, you now actually have a project file for this. So you can see here a WCP is a project file. You need to create one of these and then import the PLD files here, or it will automatically find them. You can now do the configuration options on a project basis. You may need to go in here and actually enable some of the output files to produce the document file output, for example, and for the minimization or optimization. Device selection is part of the project creation, and you can choose a particular package type and what the various options. That was a pin keeper option. Some of the options need a little bit of explanation, but fortunately the help provided is quite good. There's much better help information now provided, and in fact the device options and CUPL extensions is actually much more up to date than some of the documents that I went through in the original PLD series. This actually explains what the different options are for the different chips. So if you're doing anything with PLDs, I'd recommend you have a look at WinCUPL II. I haven't had any problems with it so far, no crashes or anything like that, so that's been a welcome improvement. When I was looking at some of the logic analyzer traces from the previous video, I was finding occasionally that you would get the odd phantom read occur before the actual floppy disk controller had actually read any data, and this caused problems when the data was then written to memory because the data was offset by a number of bytes. Went through and had a detailed look at this, and you'll see here there are a number of oscilloscope traces and logic analyzer traces. So the top trace here is where we're actually getting the chip enable signal for the particular I/O address range in the 300 series. And you'll see here that from the main bus, it's actually a very clean signal, but the output from the external I/O decoder PLD has a little bit of a blip there. I originally thought this might be causing some of these early reads to occur. If this blip was larger than normal, then sometimes it might have actually caused things to occur too soon. And in fact, when looking at the logic analyzer output, you can see here where we've actually got a floppy disk controller read period between this period here. You can see that the I/O read here is going between A1 and A2 here, but actually the floppy disk controller enable signal, which goes in to provide some enables, that was actually a gap here and a little pulse down the bottom here. So we got about a 30 nanosecond gap, then a 10 nanosecond blip. And I think under some circumstances that actually could have caused some of the problems. So by improving the decoupling capacitors, then the blip did reduce, although sometimes you could still get a bit of a blip in there. And you can see here that the trace here, that when this peak is actually as high as this, then it could possibly go into the high area of the voltage range, so potentially cause a problem. Then this is the floppy disk controller chip select that I was looking at, and this probably had slightly more interference on it. Now this is just the output from the PLD directly into the floppy disk controller, so there's very little here actually interfering with it, and I'm still looking at this to try and work out what's going on. It's certainly not actually caused by the length of the wires or anything like that. There must be some other form of interference occurring here. Certainly all the decoupling and all of the bus signals all look to be okay. And then this one here is actually just comparing where we have the floppy disk controller chip select and then actually looking at the power input pins on the PLD chip. And we can see here that with the decoupling that we've got here, there's hardly any difference in the voltage actually going across the chip. So these peaks here are almost certainly not caused by the power supply. There's likely to be some other interference coming from somewhere else, which I'll need to get to the bottom of. But it seems to have reduced to a level where it doesn't cause problems on a often enough basis to actually stop the PC from booting. And this is one I did capture where this would obviously cause quite a lot of problems, but I wasn't able to reproduce this. So there is something going on somewhere, which I'm still looking into, but at this point in time I've been able to actually boot both MS-DOS 330 and MS-DOS 5 successfully. Then this was just comparing some of the other traces with the buffered address input, and you can see that in fact this buffered address XA2 input also had these spikes. And when I was looking at the output of the chip from the decoder, then in fact this didn't have these peaks in. So it looks like it's the region of the board where this interference is coming from. I suspect something related to the actual floppy disk controller signals themselves leaking back from the floppy disk into the board. And this is the XA1 input. So again, the XA1 and XA2 inputs are showing this interference on the PLD. And again, this was actually looking at the power on the second PLD here. And so where we have the spike occurring on the FCC output, the amount of interference on the power rails was not very great at that point in time. Certainly couldn't explain the blip there due to the power rails. Then this is actually looking at the output of the XA2 value from the I/O decoder. So you can see when the FTC output has this blip on it, there's no blip actually on the output from XA2. So it's likely that something's occurring near the external I/O PLD and coming back for some reason. So I'm still looking into that. I'd like to try and fix that, but it doesn't seem to be causing any problems now. Then finally, this is just the XA1 compared to the FCC output actually closer to the chip. So you can see that there's nothing coming out of the decoder chip. It all seems to be coming from the second PLD that we have in the floppy disk controller configuration. I did some testing. I made a copy of the PLD and I basically tried driving it with the logic analyzer clock signals. So I had a clock for the XA1 input and the floppy disk controller input to see what the oscilloscope values would look like. When I looked at the oscilloscope, this is the output value here. You can see there's a slight dip here, but it's not caused by the PLD configuration itself. It's the PLDs themselves, even though it's getting a fairly messy signal coming in from the logic analyzer. The output here doesn't have any of the bouncing or anything that we've seen on some of the other signals. So this is the final state of things. And these signals are the worst case ones. Most of the time, there's virtually no interference here, but there's occasional points where we do get this spike, and it's just really whether or not this is actually going to cause any potential problems with reading the data. So having done all those fixes, now going to have a look at booting up the MS-DOS 330 first, and then we'll go and have a look at MS-DOS 5.0. So just booting up here, but if you'll notice on the real-time clock line, the year has FF25, so it indicates there's a problem there. So we're just going to go into the BIOS utility and we'll just print out the configuration. You see it's still FF25 there. So we're just going to go into the date option and we're going to now put in the date as 2025-0901. Then we just need to write that and reboot it. Okay, so after a number of fixes there, I now have the system booting to MS-DOS 330. Doesn't happen every time, but it happens sort of enough to make it worthwhile moving forwards. So just boot this now. Okay, so that's booted there, and we can clear the screen, do a directory. There's not much else actually on the floppy disk at the moment, but that should be enough for me to get going, and I'll look at cleaning up a few bits and pieces and see if I can make it a little more reliable. I've also got an MS-DOS 5.0 boot disk in there, so we'll just try booting that. That takes quite a bit longer to boot up, quite a lot more disk accessing, but that appears to work. The keyboard's not working with this at the moment, so I need to look into that, but at least it certainly managed to boot enough of the operating system to get to the command prompt. So you can see that we've been able to boot both MS-DOS 3.3.0 and was able to actually go in and do some keyboard input. The MS-DOS 5.0, I haven't been able to get the keyboard input running yet. I suspect there's still perhaps some problems loading some of the later parts of the operating system I need to get into, look into in more detail. But at least I'm able to get MS-DOS running. Now what I have been looking at is thinking about what to do next in the series. So this is the high-level plan that we've been working to. So the original Nanocomp 8088 was basically a LED keypad and display running on an Intel 8088. So we could then get the basic floppy disk PC up and running. So we've managed to get MS-DOS booting from the floppy disk there and the floppy disk controller. Now originally what I was going to do is to go in to look at getting the disk controller working, updating the CGA video controller to get the graphics modes working so we could then run early versions of Windows, so Windows 1, 2 and 3. What I've acquired more recently is actually VGA video cards. This is an ISOBUS Trident VGA video card, and I've also got an ISA bus socket. So I thought it might be interesting to see if I get a proper VGA video card working with the Breadboard PC. In order to run Windows 3, certainly the CGA will only run it in black and white mode, and it would certainly be more interesting to run it in colour mode using a proper VGA card. I have looked at if it's possible to build a VGA compatible video card. So this is VGA compatible from a software point of view, all the registers and all the things like that. And it's really quite difficult to do that. The limit really probably is CGA from the point of view of using discrete logic. VGA video cards tend to have dedicated controller chips. So what I've got, this is an ISA bus edge connector, and I've made a connector for it that plugs into a breadboard here. So this is a breadboard compatible ISA bus connector. And this is a ISA bus VGA compatible card. This is a Trident TVGA 9000 card. I did actually have the first PC I had, I think had a PCI version of the Trident 9000 card, so unfortunately I threw that out many years ago, and but this one is actually an ISA bus one, so this should hopefully plug into our connector here. And so that's what I'm going to be looking at doing in the next video. So if you don't want to miss out on future videos, then please hit subscribe, and if you could hit like if you find the content interesting and useful, just helps to make the videos available to more people. Thanks for watching.